Welcome to a screencast on an introduction to pOH and K-sub-W. Okay, now let's go a little bit further with this. We've looked at H3O+ and its relationship to pH, and we're mostly going to deal with aqueous solutions, so let's continue looking at aqueous solutions. And here's a molecular level representation of pure water. Bunch of H2O molecules in there. Now, if you look closely, you'll notice there are a couple of not H2O molecules. Here we have a hydronium ion, and here we have a hydroxide ion. And it turns out, even in 100% pure water, a little bit of this happens. So if we have water out of lots and lots and lots of water molecules, every once in a while, two water molecules will combine, transfer a proton from one to the other, and produce hydronium ion and hydroxide ion. What we say is that water auto-ionizes just a little bit. It makes its own ions. It does this naturally. And it only does this, like once out of every, or about one out of every 10 million water molecules at 25 degrees Celsius do this. It's a very, very small amount, but it does it a little. And if we write H2O plus H2O as simply 2H2O, and the products of H3O plus and OH minus, and a double arrow indicating equilibrium, we have an equilibrium expression which should have an equilibrium constant. And it turns out that, of course, it does. Here's water auto-ionizing a little, written out explicitly. Here, the double arrow is written kind of representing that there's not very many of the water molecules that dissociate, so small arrow going to the right. Most of the water molecules stay together, so that's a big arrow going to the left. And the K for this is H3O plus concentration times OH minus concentration. We call it a K-sub-W for water. So this is the autoionization or ion product constant for water. And it turns out that at 25 degrees Celsius, this product is 1.0 times 10 to the minus 14th. It's a different value at a different temperature, like with equilibrium constants in general. But this relationship, H3O plus times OH minus concentration equals this constant, that's true for all solutions, not just pure water, but it's true for acidic solutions and for basic solutions. And here's a little bit of a Lewis dot structure / molecular level representation. And here's some water molecules. And one of these water molecules, only one of very, very many water molecules, will transfer a proton to a different water molecule, and so we have an acid and a base. Water actually, this molecule acts as an acid because it donates a proton. This molecule acts as a base because it accepts a proton. We produce conjugate acid-base pairs, and substances like water that can do this, that can function as both an acid and a base depending on the circumstances, or as an acid or a base depending on the circumstances, are called amphiprotic. They're sometimes also called amphoteric. So these are substances that can function as either an acid or a base depending on the circumstances. Okay, so back to pH and H3O plus, or H plus for short, concentration. Here's a pH scale once again, where we have the pH and its corresponding H plus concentration. And now we can bring in, after noting, here are some representative solutions and their pHs ranging from, in this case, 0.1 molar HCl through 1 molar HCl through 1 molar NaOH, and a bunch of common substances in between with their approximate pH values. But now we note that solutions, aqueous solutions, contain not just H plus, but also OH minus. And here is what we get. And a couple things to note: the H plus concentration times the OH minus concentration always ends up equaling 1 times 10 to the minus 14th. So 10 to the negative 2 times 10 to the negative 12th is 10 to the minus 14th. 10 to the minus 9th times 10 to the minus 5th is 10 to the minus 14th. pH is the negative log of the H plus concentration. So if the concentration is 10 to the minus 6 molar, pH is negative log of 10 to the minus 6, which is 6. And like with pH, we can also define something called pOH, which is the power of hydroxide, if you will, and that is the negative log of the hydroxide ion concentration. So if the hydroxide ion concentration is 10 to the minus 11th molar, the negative log of 10 to the minus 11th is positive 11, so the pOH is 11. And notice that just like H plus concentration times OH minus concentration always equals 10 to the minus 14th, pH plus pOH always adds up to 14. So here's a summary of the water ionization, autoionization, the ion product constant, K sub W, and the other mathematical relationships for aqueous solutions in general. So K sub W equals H3O plus concentration times OH minus concentration, and that equals numerically 1.0 times 10 to the minus 14th at 25 degrees Celsius. pH is negative log of H3O plus. pOH is negative log of OH minus. And pH plus pOH adds up to 14. So, armed with these relationships, we can now do a problem involving all of them. This question has a 0.025 molar HCl aqueous solution, and we are to determine the concentration of H3O plus, the concentration of OH minus, the pH, and the pOH for this solution. Well, first of all, note that HCl is a strong acid, and strong acids fully dissociate, so if it's 0.025 molar HCl, then it's 0.025 molar for its H3O plus concentration because of that full dissociation. And if we know the H3O plus concentration, well, that was one of the things we wanted to find out. And if we know the H3O plus concentration, then we can find the pH because pH is negative log of the H3O plus concentration. So this is negative log of 0.025 molar, and that works out to be 1.60. So now we've got the H3O plus concentration and the pH. Let's move on and find the OH minus as well as the pOH. And these can be done in a couple of different orders. In this case, I'm going to choose to use the ion product constant or the autoionization constant for water. H3O plus times OH minus equals 1 times 10 to the minus 14th. We know H3O plus, so we should be able to solve for OH minus. And when we do, dividing both sides of this equation by H3O plus, we get OH minus equals 1.0 times 10 to the minus 14th divided by H3O plus concentration. The H3O plus concentration found previously is 0.025 molar. And again, we have to do concentrations in molarity. And when we divide this out, we get 4.0 times 10 to the minus 13th molar. And now the last thing is to find the pOH. And pOH is negative log of OH minus. Having just found OH minus concentration, we can take the negative log of that, and that gives us the pOH, and we get 12.40. And then, perhaps worth noting, previously we found the pH to be 1.60. We can confirm we did things right here because the pH, 1.60, plus the pOH, 12.40, adds up to 14.00, which is what it should do. And that's it for an introduction to pOH and KW.